This video provides an introduction to estimation. With hypothesis testing, we test the reasonableness of a null hypothesis, which we reject when the p-value is less than the significance level. But a p-value only tells us the likelihood of dealing with a chance event. It does not tell us anything about the size of the effect, that is, how different the results are from the null hypothesis. Estimation is used to estimate the size of an effect or difference. It can be used on its own, as with opinion polls, or as a follow-up to hypothesis testing. We'll only use it as a follow-up to hypothesis testing. When we reject the null hypothesis, we also reject the value it proposes for the parameter. Estimation allows us to make a better guess at the parameter's real value. Our sample statistics provide our best guess. X bar is an estimate of mu, and p hat is an estimate of p. These are called point estimates of the parameter. But single values are not very accurate estimates. Samples fluctuate, so it's not very likely that x bar is exactly equal to mu, or that p hat is exactly equal to p. The process of estimation involves drawing an interval around the point estimate. This gives us a range of values, constructed in such a way that we have a high degree of confidence that the interval includes the parameter we're estimating. This degree of confidence is called the confidence coefficient, and its most common value is 0.95. This is the proportion of times in repeated sampling that the interval we create contains the parameter. It is not the probability that the interval includes the parameter, because it either does or doesn't include it. The concept of probability does not make sense in this context. Here's an illustration. The sample proportion p hat is a variable, but the population parameter is a constant. Let's assume that we know that the proportion of older women who exercise regularly is 0.65. The interval estimate is created from the sample statistic. Suppose we collect data from one sample and get a value for p hat of 0.5. The interval estimate is 0.4 to 0.6. 0.65 is not in this interval, so the probability that the interval contains p is 0. What if the sample statistic were 0.6? Now the interval estimate is 0.5 to 0.7. 0.65 is in this interval, so the probability that the interval contains p is equal to 1. We don't know what p is, but it is not variable, so the parameter is either in the interval or it isn't. The confidence coefficient is the proportion of times over repeated sampling that the interval does contain the parameter. This is the distribution of p hat when the value of p is known. I'm going to draw a series of 95% confidence intervals. When we collect data, we get one value for p hat, which falls somewhere on this distribution. And assuming that our sample is large enough, this is a normal distribution. And 95% of all values will fall between 1.96 standard deviations above and below the mean. This also means that our interval estimate will contain the population parameter 95% of the time. Suppose we get a value of p hat that's equal to p. This falls right in the middle of the distribution. If we draw a 95% confidence interval around p hat, the interval will contain p. As our value for p hat changes, so does the interval estimate, because p hat is in the exact middle of the interval. So far, as p hat shifts to the left, the interval still contains the parameter it's estimating. When it reaches a value that standardizes to a z-value of minus 1.96, the upper edge of the interval is exactly equal to p. But once p hat goes beyond this point, the interval will no longer contain the parameter. The same thing happens in the other direction. If we shift to the right, the interval continues to include the parameter until it reaches the equivalent of a z-value of 1.96, when the lower edge of the interval is exactly equal to p. Any value for p hat beyond this point will result in an interval estimate that does not include p. So using a 95% confidence coefficient, 95% of the time the interval will include the parameter being estimated, and 5% of the time it will not. The problem, of course, is that we don't know the value of the parameter. And this is all we have, p hat and an interval around it. This is the formula for a confidence interval involving proportions. We start with p hat, our best guess at the population value. Z and the standard error are multiplied together. Then we subtract and add this product from p hat to get lower and upper limits on the estimate. The value for z is determined by the confidence coefficient. To summarize, our sample statistic is a point estimate of the population parameter and is the best single guess at this value. However, it's not likely to be equal to the parameter because samples fluctuate. An interval drawn around this point provides a more accurate estimate. The interval is drawn in such a way that we have high confidence, 90% or more, that it captures the parameter. This confidence or accuracy of the estimate is called the confidence coefficient and is the proportion of times in repeated sampling that the interval contains the parameter.